This video was produced for the Cal Maritime students enrolled in the EPO 322 Diesel Engineering 2/Simulation course. It is on mechanically actuated high pressure fuel pumps. The port and helix pump, which is the engines on the Bear, use a pump very similar to this, both for the main engines and for your auxiliary diesels, the MAKs. The standard port and helix pump, which has been dominated the industry for quite a few years. Now, the thing about these pumps, and one of the things to note on this, is that the fit between the pump plunger and the barrel is only about 7 to 9 microns on distillate fuels, which is a very, very tight fit. A micron is a millionth of a meter. 1 micron is much, much smaller than 1,000, say. So these are very tight tolerances. The pump barrel, again, the barrel and the plunger are sold as a set. They can't be replaced separately because the tolerances are so great. The effective stroke of the pump is controlled by the helix. Now, we've talked about this, and this is just a short review and to talk about some of the more advanced concepts. But when we're talking about this helix, and this is the land. Above the helix is called the land, and it goes from a maximum width to a minimum width. And then you have your spill ports. Now, a lot of the books call them suction and spill, but in almost all the pumps that I've seen within the modern engines, there's really a suction gallery so the fuel under the inlet pressure from the system surrounds the entire barrel. So basically both of these ports at some point are suction, and both of them will be spill depending on the part of the cycle. The velocity of the fuel coming out of these ports is quite high, and they do worry about erosion of the pump body. So it is very typical for the pumps to have basically, and they call them a wasting plug a lot of times, but it's a high quality, tough steel that will resist erosion from the high velocity fuel that's exiting the barrel at the end of the pump effective stroke. And if they were to become eroded, they can be replaced separately. So there's a couple features. One of the things, if you look at in this right now, the pump plunger is beneath the ports. Injection will start when the pump plunger moves up high enough that this land covers the spill ports, traps the fuel above the pump plunger, and then hydraulically will send push the fuel out through the delivery valve. One important aspect to consider on this, though, is a lot of times people really think about that as the push is what's causing the injector to open. And in reality, what you're doing is you're sending a shock wave down the high pressure pipe, and that shock wave impacts onto the injector needle and causes it to snap open. So one of the things to create that, as the pump, and this is mechanically driven with a camshaft lobe, that camshaft lobe is going to start accelerating this pump plunger. It has to have an upward movement, and so it's accelerating when it closes off these ports. That helps that acceleration, that rapid acceleration, and then a sudden closure of the spill ports will give you that shock wave. You take and you have a rack that is going to rotate the pump plunger so that either at one extreme there's a slot typically on these pump plungers, and that slot would line up with the spill port. So as the pump plunger moves up, its effective stroke will be 0. It will not have an effective stroke. It will not pump any fuel. If you rotate the rack so the pump plunger, now you're on this side of the land, that is covering up these ports, then you're going to get a maximum amount of injection. So as this comes up, right, it comes up and closes off your spill port, that start of injector, and then as it keeps moving up until the port is exposed down on this bottom surface of the helix, injection will take place. And then once this helix uncovers the spill port, your effective stroke of the pump it ends, and that high pressure fuel will flow down and out through this spill port. If you go to this side, that's your minimum amount of land. That is going to give your idle. So you're varying the effective stroke from a minimum to a maximum by rotating the plunger in relationship to these ports. But one of the things to really think about, that the amount of lift of this plunger is set by the camshaft load. So this pump plunger is always moving up and down a set amount. So its stroke is always the same. What you're changing with the port in the helix is the effective stroke of the pump. And when the pump ends its effective stroke, that high pressure fuel is dumped back into the suction gallery of the pump. And it does have an effect and cause pressure pulsations in the fuel going to the pump in those lines. Now, one thing I note about here that we can talk about is on this pump you're seeing a groove here, another groove down here. This is actually to capture a little bit of the fuel to help supply lubrication for the pump movement. That's one of the important things, that high pressure pumps have to be lubricated, and they are lubricated by the fuel. And lubricity, which is a term used for the lubrication ability of the fuel, lubricity can be affected by overheating of fuel and making it too thin, which would cause pump seizures or excess wear. This is a common problem happening right now on changeover from distillates to heavy fuel oil in the marine industry. In many cases, it's very difficult to reduce the distillate temperature down, and because a lot of the systems circulate the fuel through the injectors and the pumps, and they're picking up heat. And in many cases, it's hard to get the distillate temperature down below about 60 C, which means that typically their viscosity is below 2 centistokes. And when you get the most distillates down below 2 centistokes, you have a lubricity problem and you get excessive wear. Also, there always will be some fuel that's dripping down off the pump plunger. You have to have that because you have to have the fuel as a lubricant, and there will be some leakage. So again, when we talk about it, here's your port and helix, and here's your rack, and then the control sleeve, which is being controlled by the control rack, will rotate the pump plunger and change the relationship of the helix to the ports. And then in this case, we have a delivery valve on the exit of the pump. This is to maintain pressure in the high pressure line, so when you have the effective stroke and the fuel pressure drops within the pump barrel, you will not have the fuel draining basically out of the high pressure pipe. And that by doing that, by lowering the pressure in that, it would make it more difficult to send a shock wave for the next stroke. So the delivery valve keeps the high pressure pipe full so that it helps propagate that shock wave. Now, one of the things that you have to have on a marine engine is you're going to have variable injection timing. In this case, what they're showing here is injection is beginning at this point in the cycle, top dead center being here, and there is the delay period to where the combustion begins. Now, on a high-speed engine with a 32 centistoke, with with marine gas oil or number 2 diesel, you're talking typically about a 10 millisecond delay. And this is with the properties of the fuel and the cetane rating. And the cetane rating is usually about 32. So this is very controlled on a clean distillate. Marine fuels, MDO or especially HFO, this is absolutely not controlled. There's a large degree of difference in the delay fuel from fuel that's even spec'd the same. So what happens is if I change the delay period, that is effectively going to change the timing. And you want the timing to stay the same no matter what fuel that you are burning. So modern marine engines are almost all, even mechanical, designed to have variable injection timing. So that you can take an indicator card like this, look at the indicator card, and change the injection timing to meet or to bring this indicator card into its proper form. In other words, that you would change the timing so that the beginning of combustion occurs at the proper time of the cycle. This is an actual indicator card of one of the APL ships, the President Arthur. Now, one of the things you can when you look at that, you can see this dip right here. Let's go to a close-up of that. So this is top dead center right here, and on a big slow speed, it's a little bit different than a 4-cycle medium or high-speed engine. Typically, a medium speed or 4-cycle engine, they typically want ignition to occur probably about 1 or 2 degrees prior to top dead center. On a 2-stroke slow speed engine, they want it about 2 degrees after top dead center. Well, this is considerably different than that. And you can see that as the pressure rises up, right there is top dead center. Now the piston's going back down and the volume's increasing. So what's going on with this? This was poor quality fuel. And when you looked at this, you would notice that all your cylinders had this distinctive feature. And again, it's kind of on this view, which is the same card, by the way. This is just a, the other was a zoom, and this is taken from further back. It's looking at more crank angles. This is, you're really looking, so minus 120 to 120, you know, you're looking at 240 degrees, where the other one was maybe 45 degrees. But you can really see this characteristic dip. Well, that's retarded, that's classic retarded ignition. I would want to be able to change my timing to compensate for that. Now, this is for the MAK that's used on the Bear is our generator sets. This is just showing you how the pump is mounted, and the fact that this is your roller follower, right? So this follower is going to ride on the camshaft lobe, and as it rises and falls, then that's going to activate the pump. Now, again, one of the problems that you can have is if that dripping is allowed to go down along the follower and along the camshaft lobe, that can cause fuel dilution of the lube oil. On timing, and this has kind of been going away, to be honest with you. A lot of the modern pumps, even if they don't have variable injection timing, they are using the accuracy of manufacturer to set this. But just realize, even going back on the older ones, you could mechanically change the timing of the pump on initial setup. This is not something that you're going to change on the fly, though. Basically, one of the things for checking the timing, there are mark on the flywheel. You would move the mark on the you would move the flywheel to line up with the mark, and then on the pump, a lot of times there was a window where you could actually see if the timing mark matched up. But this is very ineffective, and typically today you are going to always check your timing of the engine, not mechanically, but running it and looking at an indicator card. So let's switch, and we'll talk a little bit about the big slow speeds. The picture that we were just viewing was for a K98MC slow-speed crosshead engine. Very popular engine right now, 980 millimeter bore. And this is a Burmeister Wain, and your fuel pumps are located in this area, and they are driven, the drive for the camshaft from the crank is a chain drive. This camshaft lobe, by the way, though, is not the lobe for the fuel pump. This is actually for the exhaust valve. And this is the exhaust valve actuator that they're showing here. The fuel pump would be on the other side of that. And then the injectors are going to be on this area of the head, or the cover. So this is the Burmeister Wain pump. And it has some added features. One of the things that's distinctive on these is the puncture valve. This is the puncture valve up here at the top. The puncture valve gives you the manufacturer the ability to incorporate into their controls a automatic shutdown of all the pumps with a pneumatic signal. That pneumatic signal would come in onto the top. We push on this plunger. That plunger moves down, and this is, if you look at it, it's a very classic check valve. That plunger would push on that check valve, and the fuel above the pump plunger can go up this way and right back into the suction gallery. This is the suction, or this is your fuel coming into the pump, and again, it's going all the way around this barrel. And so if this check valve is open, it comes up and then back, returns back. So its effective stroke is 0. And they're going to put a pneumatic signal on this to energize that and to cause the pumps to stop injecting fuel. So this, on the Burmeister Wain, let's say you hit the emergency shutdown button. The emergency shutdown button would send a pneumatic signal to all pumps, ending their effective stroke and giving you an effective shutdown of the main engine. They will also typically put a solenoid valve in the fuel line, in the fuel system. But this, you know that all your pumps have become disabled. And this is called the puncture valve. Right? It's a puncture valve. Now if you look at this pump is a standard port and helix pump. Here's your helix, just like what you're used to on the Bear. But there's a few changes. If you look down, there's 2 racks. The bottom rack moves the control sleeve to control fuel delivery and the effective stroke of the pump, just like what you're used to. The top one is a little different though. The top one is to give this pump the capability of variable injection time. And if you look right here, you can see that this pump barrel is threaded to this control sleeve for the variable injection time. So when I move this, that thread is going to move the barrel up or down. In fact, over here, this screw is to keep the barrel from rotating. And you can see right here that slot. That barrel, this barrel can move up and down that entire slot. So I can change the relationship. By moving this rack back and forth, I can move this barrel up and down, which changes the relationship of the spill ports to the pump plunger. If I move this barrel up, then as the fuel pump plunger rises, it's going to have to go up higher to close these ports and start fuel injection. That's going to retard your timing. The camshaft lobe is going to have to rotate further to lift the plunger higher to close the port and start injection. If I lower the barrel down, what that effectively does then is lower the height of the spill ports in relationship to the plunger, and that is going to advance your timing. So this feature right here gives the pump variable injection timing capability, and this is done while the engine's running. By the way, there have been some problems with this. There are some spaces up atop to allow that to move, that if there's fuel leakage and solidification, it can bind this up. The same thing too, if you get too much fuel around this rack assembly, it can cause it to bind. So they have been having some problems with this, but my understanding is that Burmeister Wain has worked these out. Now the other thing that's interesting on this is this valve that's where traditionally you would have a delivery valve is not a delivery valve. It's called a suction valve. This pump is quite large. The one that you're seeing here is actually out of a fairly small Burmeister Wain engine. These pumps can get up on the larger engines to almost a man's height. It's a big pump, and it is delivering fuel through 2 high-pressure pipes to 2 injectors. The length of this high-pressure pipe is relatively short, though. So one of the things, a delivery valve, when I asked Burmeister Wain about it and talked to them about it, one of the things they told me is a delivery valve is only really needed when you have a long high-pressure pipe. And in fact, in the matter, most unit injectors where you have a combined pump and nozzle assembly don't have a delivery valve. And they were telling me that when you look at relative to the size of this pump and the shortness of these high-pressure lines, this is actually very close to a unit injector. So anyway, they do not have a delivery valve. They do not have a delivery valve. They have a suction valve. And the purpose of this suction valve is a little bit different. When this main engine is shut down, they want fuel being able to go into the pump and into this suction valve and up and through the delivery line to the injector. And then there is a recirculation path back to the system. So when this engine's shut down, they want fuel to be able to flow through this pump to the injectors and back to the system so that you can guarantee that the viscosity in the high pressure pump and through the high pressure line and the injector is correct when the engine is shut down. You're circulating the fuel back to a small amount of fuel back to the system to always maintain viscosity in the pump, high pressure pipe, and injector. And that is done by the suction valve. Inside the injectors themselves, there is a needle valve that shifts depending on pressure. When you're injecting fuel and the engine is running, your pressure at the injector is going to be up to upwards of 1,000 bar. But when the engine is shut down, that needle valve will shift, allow the pressure to flow back to the system. And then this will shuttle open and allow fuel to flow into the line to the injector and back. So any time that the pressure of the fuel inside the pump barrel is less than this inlet chamber, it will allow fuel to flow in. The other feature they have that's kind of different on these is what they call the shock absorber. This is mounted right to the pump, and the shock absorber itself, when the pump ends its effective stroke and that high pressure fuel blows out of these ports, it goes into this shock absorber, and the shock absorber will take that impact and take out the pressure pulsations, which means that my fuel supply line will not have to take those high pressure pulsations and will not be stressed by that. So this is a little bit different pump. Again, on this one, a little bit different design, but here's your puncture valve. The puncture valve will end your effective stroke. If an pneumatic air signal is applied, it has a suction valve here. And then on this side, this would be your shock absorber. And you can see that it's right on the inlet coming into the pump. And then here are your 2 racks. The top one, variable injection timing. The lower one, as far as fuel delivery. This is a look at the pump that's installed. This is your high pressure line. That's your injector, or the Europeans, that's going to be a fuel valve. I should use the fuel valve terminology more, otherwise you might get confused. This one goes over to the second. There's your shock absorber in the background, and it's a little bit hard to see, but you see this small pneumatic line right there. That's for the puncture valve. This is a little bit better view of the bottom of that barrel and the control sleeve, and you can see the thread, and that variable injection timing, that adjustment is made using a pneumatic cylinder. Your governor is going to move your rack setting, but in conjunction it also moves this lever, which, and we'll talk about this a little bit more in a second, but this will vary the variable injection timing, the pneumatic signal, to this pneumatic piston, or cylinder, excuse me, and vary its position. So the variable injection timing is tied into the governor. On the simulator, the Kongsberg simulator, what's really nice about this is you have all this available to you. Here is your pneumatic line to the puncture valve. You've got variable injection timing. Here's your fuel rack. Here's your governor. And then what's really good, when they're talking super variable injection timer, you can actually change on these engines the starting point is when, as the governor comes up, when does the governor start to advance the timing? And then at some point you've got to stop the timing being advanced and start retarding the timing until you get up to your full load, maximum continuous rating. So this, changing these settings, would change that ratio. Basically, as the governor moves, this arm pushes on a little pneumatic regulator, and that arm, as that moves back and forth, then that will vary the pneumatic pressure going to the cylinder. And then what happens as this moves, this arm, this is a stop here and a stop there. As this moves this way, that arm goes in until it hits the stop, pushing in this plunger, advancing the timing. But then when that hits that, and if it continues to move, then with that fulcrum, this side starts to move out, and that will again retard the timing. So this is available to you right on the simulator. This is a good drawing of one of the modern Burmeister-Wain pumps. Puncture valves up here, suction valve down here. This is actually a drain. The pneumatic line would tie in up here. One of the problems that they've been having, by the way, when you're switching from heavy fuel oil to low sulfur distillates that are burned at a dramatically different temperature and dramatically different viscosity, when they switch over to clean distillate, that can cause more leakage past the pump plunger. It can also cause oil to leak up into some of the cavities and jam this, well, I shouldn't say jam it, but more excessive leakage. You get leakage off of these pumps. The suction valves can cause leakage, and the puncture valves can cause leakage on these engines when they go to clean distillates. And what ends up happening is that reduces your injection pressure at low loads and can cause the engine to stall. Okay, so this is just a picture of the shock absorber. And this is the shock absorber again. And this is a hydraulic piston with a spring. And your fuel would come in here, and each pressure spike would move that piston and compress the spring, and that would absorb those shock waves and smooth out the pulsations in the fuel lines. So this really is, they're calling it a shock absorber, but it's really a classic piston type hydraulic accumulator. But it's mounted right to the pump. Now, this is an older style pump by Burmeister-Wain. And one of the things you notice is if the fuel leakage coming down, here's your follower, this fuel could leak directly onto the follower and directly onto the camshaft lobe. So fuel will slowly dilute the lube oil, and you end up having a camshaft lube oil system. To solve that problem with their newer pumps, they are putting in this transition piece right here, raising the pump up. So the leakage, as it leaks down, leaks under this what they're calling an umbrella seal. And very similar to what you wearing an umbrella to get rid of the rain, right? It's the rain is going to go down, or the fuel is going to leak down here and drain into this space. So this seals and causes a difference between this area and the follower. So no leakage of fuel down here, and they have a fuel oil drain. By the way, go look at the Bear. The Bear does exactly the same thing. You'll notice that the pumps are raised off the crankcase, and there's kind of an orange intermediate piece with a fuel oil drain. That's why the Bear does not need a camshaft lube oil system. So this is kind of giving you just an idea of that umbrella seal, right? You can see it here, how the leakage takes place. Close-up of the pump. Again, here's your shock absorber, pneumatic line for the puncture valve, and here's your high-pressure pipes. By the way, double-walled, right? You've got this outer sleeve so that if you have a high-pressure line or high-pressure line fracture, you will not emit atomized fuel into the engine room to cause a fire. This is, again, the effect of lubricity. And this is becoming more of a problem, and you can see the seizure here. This would cause excessive leakage and cause this cylinder to not be able to deliver sufficient fuel. And this one is basically happening or being accelerated. The wear is being accelerated because of, unfortunately, the distillate fuels being overly, their lubricity dropping down because they are becoming too thin, because they're having trouble keeping the temperature of the fuel lower than about 60 C. So in some cases, what's very interesting now, in some of the ships, they've actually added coolers on the fuel system to reduce the temperature of the fuel when they're running clean distillate low viscosity fuels. This goes back to that problem, and I hate to see this type of thing, but on this ship they were having, and by the way, this line right here, that is what allows leakage, and here allows leakage past. These pumps are put together, by the way, with O-rings. And O-rings, under this kind of heat, and they are special like Viton and other materials, high quality O-rings, they get brittle with the heat, and with these extreme temperature changes, they have some problem leaking. Anyway, this particular unit, the variable injection timing, they were having a problem with because of the pump barrel sticking. And look at this, they just took the variable injection timing and froze it. And this is very poor engineering practice. You need variable injection timing. By the way, too, you really don't get away with this when you're going in changeover from heavy distillates, heavy fuel oil to distillates. Distillates, you better have your variable injection timing working, or you're going to have a lot of trouble. Burmeister Wain engines on startup go to full advanced timing. Soon as the engine starts, then the timing is retracted to help with the start process. It's not critical with heavy, it is critical with distillates. So, and there is a write-up, by the way, in the manual, and it is good when you're talking about this variable injection time. And unfortunately, again, I don't have a lot of time to spend on it. But what I want you to understand is the governor moves this arm. As this arm moves, it will push on this plunger with the pneumatic control signal, which will change the position of this pneumatic cylinder. As that continues to move, when it hits this fulcrum point, then what it happens, like they're showing here, it's shifting this way, and then it's actually moving away from the plunger to retard it. The major thing for the students to understand on this is that as you increase the load on the engine from a low load, it's usually about 30 to about 80% load, they're going to advance it. After 80% load to maximum continuous rating, you're going to retard it, and that is to give you better fuel economy. Advancing the timing at low loads will increase the Pmax in the cylinder. Increasing the Pmax at lower loads helps to give you better combustion, better atomization. And this is just a close-up of it. Again, this is your governor, and then you can see how these two fulcrum points are adjustable. So where on the Kongsberg you're putting a number in real life you're adjusting these fulcrum points to change your timing. And this is the little pneumatic, and again, this arm moving back and forth, hitting these fulcrum points, will cause this plunger to move back and forth with the action of the governor. So this is where it's showing it, right? This is where at low load, and I'm going, and the governor is moving this direction, that's going to push that plunger in and advance your timing. Break point is where both of these, now it's flat, right? And if you keep moving, you see how it shifts back. Well, that's going to retard it. So what they're showing here is Pmax. What you're doing is you're raising Pmax artificially, and then you're flattening it out from about 85% load to maximum continuous rating. And that gives you better fuel economy. The problem I was discussing before about some of the problems with leakage, and this is inability of the governor to control engine speed due to its inability to move the rack, but caking up a fuel. Again, heavy fuel oil can add some very serious problems because of the properties of the fuel and the fact that it can coke and become hard deposits. Okay, we're going to switch over to one of my favorite pumps, and that's the Sulzer pump, which is a high-pressure valve control pump. This is not a port and helix pump. It's been used for many years. It's really a great pump. Some of our students have a little bit of problem in understanding it, but it isn't that hard. It is actually quite easy. It's just your mindset. But on this, the pumps are down here. Now your injectors, your fuel valves are up here. So you can see the length of the high pressure pipe. And this is not desirable, to be honest. But the other thing, you notice that these are identical length and mirror images of each other. This pump housing right here contains two high pressure pumps, and on either side these are the exhaust valve hydraulic actuators. So two pumps and two hydraulic actuators in one unit, and they did this for cost. This shows the camshaft drive, and these are gear drive, which I personally prefer to a chain drive, to be honest. But anyway, these pumps are done two at a time to reduce cost. This is common in hydraulics, not so much in high pressure pumps. So on this, and we're going to talk about this top block first, this piece up here. So what that is, it's a solid block of steel, and they put it on a CNC mill, and they have cartridges that go in, and you bore holes in that as part of the forming this very stiff hydraulic assembly. This is, by the way, very common in hydraulics for control valve blocks. But anyway, in here is your suction valves, and they are operated by a push rod. In the center, and we're going to go through this, but in your center is your mechanism to lift the suction valve. It's called the safety cutout, and disable the pump. This here is right above the pump plungers. The pump plungers are plain. There is no helix. These are above the suction valves. These are above the spill valves. So two pumps. in kind of a mirror image. By the way, on these two, what you're seeing here, and if you look up here, those are high-grade steel Allen screws. And think about the pressures involved when you have screws that are almost touching each other. So here's a picture of the pump and equate. So this right here is this right here, right? This block in here is this in here, and then down below is here. This is your camshaft lobe. There's your follower, and here's your pump plunger. You have a suction valve and a spill valve. And these push rods activate those valves through these linkages. And this is called a valve-controlled pump. The other one of interest, and you can see them here and here, you can disable, on modern slow-speed engines, you can disable the fuel pump on one cylinder. Basically, and I won't go into the process because it's a little bit different from each engine, but while this engine's running, you can activate this. And when that follower moves up and hits its max right on the nose of the camshaft lobe at its maximum lift, this will snap in and prevent the follower from coming down and disable the pump. You can literally disable your high pressure fuel pumps with the engine running under load if you wish to. Alright, so this is a good drawing of it. Again, on here, you are going to have this is going on this particular one. This is going to be your suction valve. This is your spill valve. This is your delivery valve, pump plunger, and barrel. These caps above are how you access this. You literally take all those socket head screws off, pull out this plug, and then you actually go down and you fish out these little suction and spill valves. Same thing with the delivery. This is a little bit simpler drawing that makes it a little bit easier to understand. Here's your camshaft lobe. Here's your follower. You're on your base circle. This collar engages these two levers. These levers will rotate on these fulcrum points. So as this moves up, that part of the lever moves up, and the lever itself is going to rotate around this fulcrum. So as this moves up, that push rod will move down. But look at this. This one's outside the fulcrum point. This one's inside the fulcrum point. So it is reversed. As this pump plunger moves up, that push rod is going to move up. And it's a little bit hard to see on here, but there is a space between that push rod right now and that spill valve. They're not touching. This one is, in fact, at its, when you're on your base circle, that's going to be at its maximum height, and it's going to lift the spill valve off the seat. Now the fuel is coming in, and it's flooding in this gallery and above the pump plunger. So all of this right now, because that suction valve is open, and these are little check valves, by the way. It does act as a check valve. But the fuel comes in and floods this. So this whole area is going to be at inlet pressure, fuel system pressure. Now, as this starts to walk up the flank of the cam, and these levers are coming up, this lever is coming down, and it drops that suction valve on its seat, which is what you want. Again, the same thing with covering the ports. You want the pump plunger to be accelerating, and then all of a sudden, you want a very sudden closure, and so that you will give yourself a shock wave, and that shock wave, since it can no longer, the spill valve is closed, the suction valve is closed, it can't be spilling as the pump plunger moves up, it can't spill back to the suction, it's trapped. So it's going to go out the delivery valve to the fuel valve. Okay? So a very sudden start of injection is what you want. Now, as that continues to move up, this spill valve push rod is moving up, and at some point it is going to lift the spill valve off its seat. As soon as it lifts the spill valve off its seat, then that high pressure fluid is now going to be released back to the suction valve. So the suction valve closure, suction valve closure is start of injection. The spill valve opening is end of injection, and injection only occurs when both the suction and spill are closed. Now, in a modern electronic engine, by the way, this pump is still popular, but instead of having two valves to control this, you use one because you're using a solenoid. The reason that you had two in here is because of the levers and to be able to do this mechanically. But if you're doing it electronically, you would basically put a solenoid on one of these valves, and closure of the valve is start of injection, opening the valve is end of injection. Now, how do we change this? Well, you can have an eccentric. Now, one of the things I want you to look at this, you've got a round rod, and then you've got this nipple on the end, you've got this protrusion, but it's not in the middle, it is on the edge. So what happens is this rod extends out the back of the pump, and there is a lever on that, and when you move the lever, that lever will rotate this eccentric to the bottom or the top. And I can do it depending on the pump, on the design. I can do it both on the suction valve and the spill valve. So let's talk about the suction valve. If I rotate this all the way up to the top, that will mean that on this case, if this is all the way up to the top, then we're on our base circle. That is going to be higher, and that's going to hold the suction valve up farther. And I'm going to have to go up, the follower will have to travel farther up the flank of the cam before that drops onto the seat. So that's going to retard your timing. If I rotate this down to the bottom, then that suction valve is going to be closer to the seat, and it's going to, as you go up the flank of the cam, drop onto its seat much quicker, advancing the timing. On the spill valve, if I rotate this to the bottom, there's more gap up here. Means the pump plunger has to move up farther before it touches the spill valve. That's going to maximize fuel delivery. I rotate this up to the top, it's going to be closer to the spill valve, and so as I move up the flank of this cam, it's going to touch much quicker, and that would minimize fuel delivery. So the suction valve eccentric gives you variable injection timing, and the spill valve eccentric gives you the amount of fuel delivery, the effective stroke. It gives you a longer or shorter effective stroke. And one of the things on this is with these, the start of injection is when the suction valve drops on its seat. End of injection is when the spill valve is lifted off its seat. Now, one thing, because I forgot to talk about a little bit earlier, and so I want to quickly go over that. Let's go back to here. Okay, the port and helix pump, one of the things they say is that it's time from spill port closure. As that pump plunger moves up, when that land from the pump plunger covers these spill ports, then that's start of injection. So when you're talking about timing, these are timed for spill port closure. In fact, with these, when you're doing it mechanically, what you would literally do is take the top, the high pressure pipe off, take the top of the pump off, and supply low pressure fuel, just like out of a coffee can, into the inlet of the pump. And as you rotate the flywheel, you would have oil leaking out the top of the pump. Until, if I'm supplying fuel in here, it's going to, whoops, the delivery valve is gone, this top of the pump has been removed, the oil is going to come in and leak out until the pump comes up the plunger and covers these ports. You would stop at that point and go look at your timing to see if you were at the mark. So they were, a lot of a common term is the port and helix pump was timed for spill port closure. Alright, so this is where your barrel would go. This is your spill valve. This is your suction valve. Another interesting feature of these Burmeister, Sulzer, this was the Wärtsilä pump, was they put a relief valve. It's the only high pressure pump I have seen with a relief valve in it. This is to protect you in case the fuel in the pump is too viscous for delivery. Rather than do damage to the system, this would open and blow the oil out into the engine room. And I've seen this happen. It was quite impressive. But what had happened is we'd lost our boiler. We'd lost steam to heat the fuel up. The fuel became too viscous for injection, and the safety valves opened up and blew out that pressure to prevent us from damaging the high pressure fuel system. Most engines out there do not have that feature, and allowing the viscosity to get too thick for injection, you are going to do major damage. It's a hydraulic system. Without a safety valve, something's got to let go, whether it's the follower bends, whether it's the camshaft lobe is dented, whether or not you blow the pump off its foundation. Anyway, these Sulzer slow-speed engine valve control pumps had a safety valve to prevent that from happening, or to minimize the chance of it happening. The safety cutout device, what this does, this is the pneumatic piston. When I put air on this, it goes underneath that piston, lifts it up against the pressure of a spring, it lifts up this fork, and that will actually lift up the push rods for the suction valve, lift them off their seat. And by the way, this is a good view of what the suction valve looks like, and the sealing surface is right in here. These would lift for the pumps, suction valves off their seats, and you could disable the pump with a pneumatic signal. So if you did not have, if the older engines, you only had the governor controlling your spill, your beginning of injection was always the same. This was a non-variable injection timing engine, but your endpoints were different. And as you change that, you have more fuel delivery and you control the output of the engine. But the more modern engines incorporated into this also for your suction valve to give you the variable injection timing. Now, on this, as the governor moves, this fulcrum would move, and it is, you see this cam. This cam would change the variable injection timing as the governor comes up. Just kind of what I was talking in the Burmeister wing. You're going to advance the timing from about 30%, usually up to about 80% load or so, and then you're going to retard it from say 80-85% up to 100% maximum continuous rating. The change of that was because of the shape of this cam. It also had a fuel quality setting lever. What this means is you could change the timing of the pumps, all of the pumps, by moving this lever to accommodate for fuel quality. So if you had a more ignition delay, you could take and advance the timing to bring your timing back into play. So anyway, that's why the variable injection timing and the governor are tied into each other to give you that. The other thing on this, that's why this engine, you can have a variable from start of injection, right, and end of injection to control the timing of the pumps depending on ignition delay, fuel quality. And this is just a real look at the linkage system on these. And again, this is that rod that I was talking about that goes through. And these are the control arms. And here's your fuel quality setting lever. and this cam will adjust for the timing depending upon load of the engine. And that's it. Thank you very much.